So now that we took a look at those infinite limits that typically result in vertical asymptotes, we're going to go ahead and move on to limits at infinity. That's where the limit is, or has the variable approaching either positive or negative infinity. So if you think about this graphically, if the x's are getting very, very large or very, very small, you're analyzing the end behavior of the graph, what's happening all the way to the left and all the way to the right. And there are some strategies we can use to help us analyze the end behavior of a function. One thing you can do is look for the highest degree in standard form, because if you were to think about plugging in infinity into those x's, we can't really do direct substitution with infinity. It doesn't work the same way as it would with a numbered value, because infinity is not a number, it's an idea. It represents a number, but it's not a physical number itself. So what we can do is, if we were to think about plugging in infinity, notice how this term, because it's cubed, would be affecting the value more than these other ones, because you just have a single x and then a -4. So if you're plugging in a really, really, really big number, this is going to be gigantic because you're cubing it. So then these are kind of insignificant, because they're much, much, much more smaller values than what this one would be. So what we can do is just take a look at this term and think about how would, or what would that look as we go forever to the right. So if you take a look at this term, notice how it's a negative cubic term. So graphically, a negative cube, well, first of all, a positive cubic would look something like this, and if it's a negative, it's going to flip upside down, so it would look like this. Very similar to how we did those exponential functions where we thought about the graph and how the changes affected the shape. We can do the same thing here. So graphically, the further we go to the right on this negative cubic graph, we would be going down. So this limit value would be negative infinity. Now, the only way we can look for the highest degree is when it's in standard form, meaning there's no parentheses. We typically write the highest power first, and so on and so forth. So if you look at the next one, this one is not in standard form. This is what's called factored form, because you have those individual groups being multiplied together. We can think about what the highest degree term would be if we were to actually multiply this out. Now, I'm not saying you have to multiply it out. We're just trying to figure out what that leading term would be. So we can kind of break it apart here. Notice how we have a negative x squared times another x times another x. All the other values are going to be insignificant because we're plugging in a very, very, very negative number. So if you're subtracting 3, adding 1, that's basically insignificant. We are worried about the variables, though, because those can get quite large depending on what your degree is. So if we have a negative x and we square it, that would be a positive x squared times another x would end up being an x to the 4th. So graphically, an x to the 4th graph kind of looks like a W shape, kind of like that. So the further we go to the left on this graph, it looks like we would be going up, so our limit value would be positive infinity. Now, what can get a little tricky is when we're dealing with fractions, because notice how we do have 2 degrees going on here. We have the degree of the top versus the degree of the bottom. Again, if you're adding 3, that's pretty insignificant when you think about substituting in infinity. So we're not really worried about the constant terms or any other values. We're always looking for that highest degree. Now, if you think about this, we have negative 2x over x, and that would simplify because the x's would cancel out to negative 2. So we actually have a limit value in this case not going down or up. Notice how the further we go to the right, this limit is stating that we are approaching negative 2. So this value is representing a horizontal asymptote specifically to the right. So on the right side of this graph, we're going to level off at negative 2. It's not too bad when you're dealing with these polynomials because we can just look for the individual highest degree, but when we start talking about fractions, we will have 2 to analyze, one from the top and one from the bottom. So we're going to briefly review those rules for the rational functions, okay, those fractions. We did go over them last year, but again, they might be a little fuzzy, so that's why we're going to take a look at them now. So we're always going to be comparing the degrees. We're going to say if the bottom degree is less than the top degree, what would that result in? What if the bottom degree is greater than the top degree? And the last combination is what if the bottom degree is equal to the top degree? So if we think about it, if the top degree is higher than the bottom, we have a very fast growing function divided by a slower growing function. So if the top is getting very, very large, whereas the bottom is not growing as quickly, you're going to have a really big number over a much smaller number. So a big number divided by a small number is still going to be a very big value. So you're probably going towards infinity or negative infinity somehow, depending on your direction. So in this case, if you're going up or down on the left-handed side, we do not have a horizontal asymptote. But if we don't have a horizontal asymptote, we perhaps have a slant asymptote. And we'll take a look at an example of that in a second. Okay, this is for rational functions where we have those fractions. Let's say that the bottom degree is bigger than the top. So this is when we would have the slower function up top and the faster one down below. If we think about this numerically, we're going to have a really big number on the bottom versus a smaller number up top. So something small over something huge, if you were to divide those values together, you're getting closer and closer to 0. So in this case, we have a horizontal asymptote at the y value of 0. The last thing is if the bottom and the top are exactly the same. And we kind of saw that here in the first example. Notice how the degree of the top was 1 and the degree of the bottom was also 1. So since those degrees matched, those x's we could think would cancel out, and we're just left with the ratio, the division of those coefficients out front, meaning -2/1. And notice how this represented a horizontal asymptote. So if this is the case, if they're equal, we do have a horizontal asymptote, and it's specifically at the y value of the ratio of the coefficients. So we'll just divide those numbers out front.